So here's our second example on working with domain, and I actually pulled 3 problems from homework 4, problems 13, 15, and 16. And I'm actually not going to do these in order. I'm going to do 13 first, then 16, then come back to 15. No particular reason. I just want to talk about something that happens in 16 and use that to build for number 15. So number 13 looks an awful lot like the example we just worked out in the previous lesson. So here we need to be watching out for division by 0. We have 1 divided by x minus 8, and we want to make sure that the denominator is never equal to 0. So that means that we don't want x to be equal to, x minus 8 to be equal to 0, so x cannot be 8. So just because I want to make this picture so ingrained in your brains that it is what you think of when you think of functions, if I were to try to input 8 into this function, it would not know what to do with it. If you tried to use a calculator, it would output an error. So everything else is fine. The only time you're going to have a problem here is when you try to divide by 0, and the only time that you're going to try to divide by 0 is when the value of x is 8. So when we're talking about possible inputs, the only one that's out is 8. So the domain is all real numbers except for 8. And it says here in the instructions, enter your answer using interval notation. So in your answer, you would put from negative infinity to 8, skip the 8, and then from 8 to positive infinity. Again, skipping the 8. Okay? So that is the first example. So what I hope I'm getting across here, and I'm going to summarize this at the end of this lesson, is for our purposes, division by 0 is one issue that we look out for with domain. And if there's a division happening within the function, we want to exclude any values of the input that would cause division by 0 to happen from the domain. So now we move on to number 16, and number 16 is significant because it has the other issue that causes us to exclude things from the domain, and that is square roots of 0. Of negatives. So remember, our functions are functions that take real inputs in and put real outputs out. Everything is in the real numbers. And as maybe you already know, or maybe you faintly remember, and if neither of those things is true, we will talk about it later on. Square roots of negative numbers are perfectly lovely. They absolutely exist. They just exist outside of the field of real numbers. So if we're restricting our functions to operate only in the land of the reals, square roots of negatives are a no-go. So whenever you encounter a function that has a square root in it, notice I'm being very careful to say square root, not radical symbol. Because number 16, that function has a radical symbol in it too, and it's a very different story. But we'll get to that in a second. It's not possible to take the square root of a negative and get a real number. So what we need to say here is, well, since we have a square root happening in this function, square rooting is part of the rule of this function. We need to make sure that that which is underneath the square root is not negative. So it can be positive, it can be equal to 0, but it cannot be negative. Okay, so this takes us back to the land of nonlinear inequalities, which was our jam in week 2, right? We got really, really good at these. This is a nonlinear inequality. So the first thing we're going to do is either factor this, or I suppose you could just find the critical numbers and go from there, but I'm going to go ahead and factor it. So x squared minus 64 factors into x minus 8 times x plus 8. So the critical numbers are 8 and negative 8. I'll just write plus or minus 8. And then when we go to build a sign chart, I will notice here that I don't have any non-negative factors, which means that as soon as I figure out the sign in one of the regions, it'll just flip-flop from there. So let's test 0. 0 is a favorite of ours to test when it's not a critical number. X minus 8 is negative when x is 0. X plus 8 is positive when x is 0. So their product is negative. Since there are no non-negative factors, the sign will just flip around each of the critical numbers. So that means it's positive to the left of negative 8 and also positive to the right of positive 8. Remember, we said that what we're looking for are the values of x where x squared minus 64 is either positive or 0. So that means for our purposes, we're looking at these guys, and we're looking at these guys, and the endpoints themselves are included. So negative 8 and positive 8 are both included. So in interval notation, we would take everything up to negative 8, including the negative 8, and then everything starting at 8 forever on. So from 8 to positive infinity. So that's the domain of this function. Let's move on to number 15, and then we will summarize what we observed here. So number 15, at first glance, there's also a radical, so that may make you feel like, oh, this is very similar to number 16, same idea, but in fact, there's something significantly different. And that is that it's not a square root. This is a cube root. And I'm going to write that in big red letters. This function takes a cube root. I'm sort of hoping that you've seen cube roots before, just because it's one of the things that's theoretically covered in Math 60. So I'm not going to review it in huge length, but I will just point out here that the way that a cube root works is it's asking whose cube is this number. So for example, the cube root of 8, what would you multiply 3 copies of and get 8? Well, it so happens that the cube root of 8 is a rational number, it's just 2. Okay? By that same token, the cube root of 1 is the number that you would multiply 3 copies of together and get 1. The cube root of negative 8, right? So this is kind of a moment that might challenge some of our comforts. But as it turns out, if you just take negative 2 and multiply 3 copies of it together, negative 2 times negative 2 times negative 2, you end up with negative 8. So cube roots are totally happy with negatives. They don't have that same restriction. So in fact, the cube root of a negative number is just the opposite of the cube root of its positive counterpart. So when we're talking about radicals, we have to pay attention to the index. This number here, this 3, is called the index of the radical. And if it's even, like 2 or 4 or 6 or 8 or 12 or anything like that, you have a problem with negatives. If the index is odd, you couldn't care less. So you'll notice in your homework, there's a problem that I'm not doing here that actually has a 4th root. It's a function that takes a 4th root. I think it's something like the 4th root of x squared plus x. And that is another radical with an even index. So again, you need to be careful about negatives. But if the index is odd, you don't care. So there are no divisions here, so you don't need to worry about division by 0. The radical doesn't have a problem with negatives, So even though at first glance this function looks like it'll have an issue with the domain, in fact it does not. So this is an example of a function whose domain is all real numbers. So in Webassign, what you would do is you would input from negative infinity to positive infinity. Now really quickly, since we're still in this lesson, I want to show you a quick Webassign shortcut. So I'm actually going to open this homework in Webassign, and here is, let me navigate to this problem. So this is number 15, and sure enough, the math pad comes up again, and sure enough, I'm not a big fan. So what I do when I want to type the infinity symbol into Webassign, incidentally, it's in the symbols menu in the math pad, but I just go, so I need a parenthesis, so shift 9, and then negative infinity. So I'm going to type I, N, F, T, and as soon as I type the Y, oops, maybe I need to type out the whole word. There it is. Sometimes just inft works, but so let me show you that one more time. I-N-F, I-N-I-T-Y. So just type out the word infinity, and then since we're going from negative infinity to positive infinity, we'll just do that. So that is the domain of this function. Since I'm in Webassign, let me just quickly scroll down. And you see here, there is that problem that I was talking about where you have a fourth root. It's the fourth root of x squared minus 9x. So that's an even index. So you're going to have a problem with negatives. So you want to make sure that the inside is greater than or equal to 0. Number 17 is another problem that I'm leaving off for you all to explore. Notice that it's a combo, double whammy, right? On the one hand, it has a square root in it, so you want to make sure that the thing under the square root is greater than or equal to 0. On the other hand, you're doing some dividing, and you want to make sure that the thing you're dividing by is not 0. So I'll let you play around with numbers 17 and 18 on your own. Of course, if you're having troubles with them, bring them to office hours or bring them to our meeting on Friday. So in the last couple of seconds of this video, I just want to make a quick summary, and I'll put it up here. And this will be a living summary. So as our arsenal of functions expands, so will this list, but not by very much. When looking at domain, when looking at the domain of a function, so again, this is not an exclusive list. This is just our list so far. We will add to it later. We want to avoid division by 0. So look at your function and determine, is there a possibility in this function where I might be dividing by 0? So like 1 over x minus 8 is a prime example. So the second one, I'm going to say this: avoid allowing negatives under even index radicals. So even index radicals are square roots, fourth roots, sixth roots, and so on. I very much doubt that we'll encounter any sixth roots in our work, but we might. And as you can see, there is a problem in your homework that deals with a fourth root. So that's a quick summary of working with domain. Notice I didn't mention the range at all. We will talk about range again later, but domain is what we're going to focus on in this lesson. That's all I have for you. See you later. Bye.